Hello and welcome back to me answering questions from Algebraic Geometry by Robin Hartshorne. Today we will be answering question 1.4 of section 1, and today is a topological question as opposed to what have been doing so far. So let's just get stuck into it. So this question wants us to identify the affine plane with the affine line in the natural way. So let's just the affine plane AK2 is x times y, given that x and y are in K, but this K is essentially as a set equivalent to the affine line. So uh, the affine line is our field with the Zariski topology on top of it, technically also with the structure sheaf, but that's well down the line. But it is here. So as a set, we can just replace that k with the affine line and say, oh look, it's as a set the same as a k1 times a k1. We need to show that the Zariski topology on the affine plane is not the product topology of the affine of the affine line. Now, first of all, what is the product topology? Now, considering we are working with a finite product, the product topology and the box topology are the same thing. So I'm just going to say it's the box topology. So what we are looking for is the product topology has as its open sets U equals U1 cross U2, where U1 U2 are open subsets of the Zariski topology in AK1. Now we should probably describe what this is. So first of all, within algebraic geometry, K is always an algebraically closed field. So U1 and U2, I should now define the Zariski topology. It has as its closed sets the vanishing sets of subsets of your coordinate ring. So let me let me see. So given a function in k adjoint x, we can decompose it into linear factors. So f equals k naught times x minus k1 times x minus k2 times dot 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 times x minus kd, where d is the degree of f. Therefore, v of f is going to be the union of uh, I equals 1 to d of v of x minus ki, i.e. it is going to be the set k1 dot 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 ki. Therefore, as a Zariski open subset of the affine line, AK1 is going to be a Zariski open subset of the affine line is going to be AK1 without these points. So K1 dot 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 KD. This is meant to be a D. So what we are looking at with the product topology is, say, this point, and this point, this point, and this point, and this point. This point has been removed, so we draw these lines here, these dotted lines, to say that our product open subset is of this form. So, one thing which we can show about this is let Y be a product open thing if the following points A, B, and B, A are in Y. For instance, let's say here is the diagonal. Very bad diagonal, I know. If this point and this point are within our set, then the A and B are going to be within U1 and U2. Right? So these are going to both be within these points. Now, how can we use that fact? In fact, I shall go to the next page. Let Y equals U1 times U2. If A, B, and B, A are in Y, then A and B are within U1 and U2. In U1 and U2. So, let us consider the Zariski open set AK2 minus the vanishing set of x minus y, or visually, it is the affine plane minus the diagonal. Well, if x and y are distinct numbers, then xy and yx are within our, let's call this z, are within z. Because, well, they're not the same, so they are mirrored across this. You see? Well, therefore, if our Zariski open set is the x minus y, if our Zariski open set is indeed product open, then it is U1 times U2. But what we have shown here is, well, all of K must be within U1 and U2 So if it is of this form, then AK2 minus our vanishing set, x minus y, equals AK1. What is, sorry, that does not equal to, minus our vanishing set is AK1 times AK1, which we have canonically identified with AK2 as a set. The affine plane. So the affine plane minus this vanishing set, which we know is not equal to the affine plane, is equal to the affine plane. This is false. This is a contradiction. I've forgotten what the sign for contradiction is. I think it's like that, but I could be wrong. But either way, we should just write this is false because it just is, because this contains the point 0, 0 and this doesn't contain the point 0, 0. Hence, one of our premises is wrong, and that premise, the only thing which we have actually supposed, is that it is of this form. Therefore, thus we have found a Zariski open subset of AK2, which is not product open. Hence, we have shown that these topologies are distinct. Smiley face, and I guess QED. Oh, I thought that I had more space, but I don't. Anyway, as I guess is customary, I will say thank you for watching. Smiley face. This is me. Okay, thank you for watching. Goodbye, until next time.